All right, we're going to try to get through this pretty quickly. I want to go through circular motion. And we've been spending a lot of time this year talking about things that are going in a straight line. And we've talked about projectiles, but this is when something is going in a circular motion and continues going in a circular motion. And so we have to take some of the things we learned previously, adjust them slightly to make sense of them. So what we're going to look at is how do we describe circular motion? And we're going to still go back to Newton's second law and say how does Newton's second law apply to the circular motion? And how can we model, calculate forces? How can we calculate acceleration when we're talking about circular motion? The main vocabulary word that we have with this is centripetal, and that will come up here in a moment. And it's kind of a key word in what we're going over right now. Okay, so obviously objects can travel in a circular motion, not just a straight line. And there's a couple different ways that they can do this. One is through rotating, and the other is through revolving. Sometimes these are kind of confusing. Rotation is when something is simply spinning. So if this marker is spinning around like this, we would say that it is rotating, whereas a revolution would be more of it's spinning around some kind of a central point. So you've got the word axis, and the axis is where it's spinning around. If it's rotating, the axis is inside of the object as it's moving. And if it's revolving, then the axis is the middle part that it's actually going around. Think about the Earth. The Earth rotates each day when it spins, but it revolves around the sun each year. So both of those are circular motion, and they can be explained in these ways. So when we're looking at circular motion, we still have to get into forces. So in order for something to move in a circular path, then there has to be a force exerted in order to keep it in that circular motion. The force points to the axis of rotation. So again, if we had an object going in a circle, it's rotating around this black point right in the middle. That's the axis of rotation. Therefore, the forces are pointing towards that axis inward, kind of pulling it in that direction. Now, obviously, the object itself is not moving inward. The object itself is following a curved path. And as it's following a curved path, it's basically doing two things. It's trying to get pulled towards the center, but at the same time, it's also wanting to, with its inertia, to kind of fly off in this direction, the way that my arrow is pointing. And it ends up kind of traveling a path that's in between, which is represented by this red arrow. So the inertia wants to keep it moving outward. The force is wanting to pull it inward. Its path ends up kind of being somewhere in between with that. As that continually happens, we get a circular path. I mentioned earlier the word centripetal is going to be important here. So centripetal force. And so this is the force that's directed towards the center of the motion. It can be represented with a capital F and a little c, the capital F for force, the little c for centripetal. And the centripetal force can be a number of things depending on the situation. So tension in a rope, for example, if you're swinging something around, that could be pulling it into the middle. You could be having gravity. So obviously there's no rope that's there, but the force of gravity could be pulling the object towards the center. And if you had something spinning on a flat surface, for example, a merry-go-round or something on like a record player, the object might not fly off because of the friction that was holding it in place. So each of those can be examples of forces. Again, capital F for the force, little t for tension, G for gravity, F for friction. So we can kind of point out what kind of force it ends up being. Okay. So the object, when it's in circular motion, the object itself wants, think of it that way, wants to go straight because of inertia. Inertia says an object wants to continue its motion until an outside force acts on it. So if we were spinning something in a circle and in that point where it says 1, the object wants to continue going in the direction of this red line. However, it's the pull in that's going to kind of keep it from doing that. And if we remove the force, if you're spinning something around and you just let it go, it would fly off in this direction that's indicated by the red arrow at 1. Similarly, if we let it go around to 2 and we let it go at that point, it's going to fly off, continue into a straight line when we remove the force. So that inward pull is constantly changing the direction. And when we're changing a direction, going back a few months, that results in an acceleration. And in order to accelerate things, we need to have a force. So there's kind of a lot going on here. There's a constantly changing velocity because we're constantly changing the direction. And in order to do that, there has to be a constant net force acting on something. And that's the net force that's being pulled in with the centripetal force. There's a video link on here if you're looking at, if you're clicking on the slides. I'm not going to show it right now for the sake of time, but it's just indicating a guy taking a glass of water and being able to kind of spin it around on a tray. and the water's not coming out. So what affects the amount of force? I mean, again, imagine if you were twirling an object around you, what would make you have to use more force, all right? Or what would cause it to be more forceful? If the object you were spinning was heavier, probably there'd be more tension on the rope. If you were moving it faster, there would be more tension on the rope. And this may be a little bit backwards from what you might think, but if the rope was longer, it actually wouldn't feel as there wouldn't be as much tension on it, assuming you were keeping all these other things similar. And so we put these things together in a mathematical formula, and what it ends up being is we take Newton's second law that we've been working with before, F equals ma, and we specifically talk about it in terms of centripetal force. So we put the little c's right here. So this is still Newton's second law. And the acceleration in this case is the velocity divided by the radius. And so, excuse me, the velocity squared divided by the radius. So again, how fast it's going divided by how big of a circle basically do we have. And so if we replace the a with this v squared over r, then the formula ends up looking like the big box right here. All right, so again, let's think about the relationships. More mass is more force because it's on top of the fraction. More velocity is more force because it's on top of the fraction and it's squared. More radius is actually going to make the force go down because it's on the bottom of the fraction. So again, we can look at the fraction to get an idea of what's going to be the effect on the force. Things on the top of the fraction are going to give us, if we increase the top of the fraction, it's going to go up. If we increase the bottom of the fraction, it's going to go down. Again, remember the top of the fraction is always a direct relationship. The bottom of the fraction is always an inverse relationship. And this is what it looks like on your formula sheet. We've talked about gravity. We've done some calculations here. This is our first formula. The rest of these are the circular motion formulas. So again, this is just what I showed you on the previous slide. So all of this is on the previous slide. This one was on the previous slide. And this one is give us an idea of how fast is something going if it's going in a circle. And I'll go through that in just a minute. But 2 pi r tells us about the distance around the circle, and t is for time. So if we are measuring distance divided by time, again, we're getting velocity. And then all those things are spelled out for you over here. So how do we end up doing the math? The easiest way to do the math is to plug in a bunch of ones, like we've done before with gravity, and to replace them in the problem to figure out what's going to be the change. So as an example of this, if we take our original formula and plug in a 1 for the m, plug in a 1 for the v, and plug in a 1 for the r, then we get something that looks like this. And then if our question says blah, 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 if we double the radius, then we go to where the r was, and we're going to change the 1 to a 2 and do the math again. And if we change the bottom of the fraction to a 2, then we end up getting an answer of 1/2. Therefore, if we change the radius from 1 to 2, we're going to get the force going from 1 to 1/2, which means that's going to cut the force in half. So if you double the circles, double the radius of the circle, you're going to end up cutting the amount of force in half. All right. What if we change the speed of a car? So if a car goes from 60 to 20 miles an hour around a curve, one of the things to keep in mind with this is we always want to look at it in terms of proportions or fractions. So if the car goes from 60 to 20, we don't want to say, well, that's minus 40. What we want to say is if it goes from 60 to 20, then that's 1/3 the original speed, right? Because it's now going 20, but it was going 60. It's going 1/3 as fast. So then what we want to do then, go back to plugging in 1 for all of this, except what we want to do now is put a 1/3 in for the v, because the velocity is 1/3 what it was originally. And if we put a 1/3 in for v and do the math, 1/3 squared ends up being 1/9, and we end up getting an answer of 0.111. So if we slow down considerably, if we reduce our speed from 60 to 20, we're going 1/3 of our original speed. And if we're going around a corner, then that's going to change the force to make it 0.111, which kind of makes sense. If you're driving a car, imagine if you're going 60 miles an hour versus 20, the amount of force that you're kind of feeling is going to be much more reduced. If we get a question about how long or how fast is something going in a circle, we're going to use this last formula down here. So if we had a record and it takes 1.3 seconds to make one complete rotation, and we know how far it is, then we can just plug in our units right here. So if we take this formula, we've got a time that's 1.3, so that's going to go on the bottom of the fraction. We've got a radius that's 0.12, so that's going to go on top of the fraction. We're going to use the pi button calculator. And so the velocity would be 2 pi times the radius divided by the time, and it gives us the speed that we have on. One of the things about stuff that's moving on a circular path, like a record player or something, is that as it's spinning, the farther out something is, the faster it would have to be going. So if I had a spinning object, whether I'm showing it to you with this marker right now, or if I were in class with a bigger meter stick or something, the farther out that it's going to be going, the faster it has to move to be able to turn around because its path is longer. So the path of the tip of this marker is a circle that's maybe this big, whereas when I spin the middle part, its path is only maybe this big. And so even though it takes the same amount of time to go around, the farther out you go, the greater the distance is. It's kind of like running a race on the track. If you're running in lane 1 versus lane 8, if you're running in lane 8, you have to cover a bigger oval than you would in lane 1. So in order to get from the starting point all the way around to the finish point, you would actually have to be running faster in order to be able to do that. Okay, had a video link on here that, just for the sake of time, I'm not going to show that right now. I think our last question here, what is the centripetal acceleration? We have a formula for that. And to find that, we need a velocity and a radius. So it says if we had a tangential speed, which you don't have to really worry about what that means too much, we have a speed which is 8, and we have a radius at 5. So we plugged that into our formula. So V over R, our V was 8, the R was 5. So put that in the calculator, we get an answer for that. All right, so in summary, since centripetal force is pulling an object towards the center, we can calculate the amount of force and see the relationships in our equations between mass and radius and velocity. So again, some of these, when some of these go up, the force goes up, goes down, the force goes down. And you can use your formula to look and see how those are by replacing them with ones. And then again, the last thing to keep in mind is the larger the radius gets bigger from the center, the faster something has to go to complete that trip in the same amount of time because the distance ends up being larger.